We're now going over the electromagnetism part 2 SAC. The first question was to describe the role of slip rings in the above device. And the key point here was that the slip rings their job is to preserve or to maintain the AC output into the external circuit. And the way that it's achieved is, if you look closely at the slip rings, which are these devices here, you'll notice that this coil, this part of the coil, is connected to this ring, and this end of the coil is always in contact with this ring. On the other hand, this side of the coil is in contact with this ring at all times. And so as the current changes direction every 180 degrees of rotation, which is what it will do, then that change in direction of the current will be reflected through this terminal here, and likewise this terminal here. So if this was connected to a circuit, then as the current changes in the coil, so we would then see current change direction in our circuit as well. So the slip rings simply preserve the AC characteristics of the current being generated in the coil to whatever external circuit we've got connected. Okay, question 2. The coil is a single rectangular loop of effective area 9 times 10 to the minus 14 meters squared. The coil can be rotated about the axis shown in a uniform magnetic field. Okay, question 2. The maximum magnetic flux that passes through the coil is this value, 7.2 times 10 to the minus 6 Weavers. What is the magnitude of the uniform magnetic field? Okay, so basically for question 2, we need to calculate the magnetic field strength, and we are given the flux, and we are given the area of the coil. So we're going to be using the formula flux equals B times A. And obviously we need to rearrange this formula so that B will equal the flux divided by A, and that will equal 7.2 times 10 to the negative 6 Weavers divided by 9 times 10 to the minus 4, and that's meters squared. And that should come out to a value of 0.008 Tesla, or if you prefer, 1,238 milli Tesla. Right, now, question 3. Now the coil is being rotated. In an interval of 0.02 seconds, the coil is rotated in a clockwise direction by 1/4 of a turn. What is the magnitude of the average EMF induced? Okay, so go up to and look again. At the moment, the field lines, the flux through the coil will be 0, and it's going to rotate 90 degrees in the clockwise direction in 0.02 seconds. So let's do that calculation. So for question 3, we know that the change in flux, it has gone from zero to its maximum value, which is what happens during that 90-degree rotation, and therefore it's gone from 0 to the maximum value is 7.2 times 10 to the minus 6 Webers. Now remember, it is flux we use here, not magnetic field strength, and I think a few people might have made that error. It's the change in flux that's important, okay? So therefore we know that the change in flux and whether it's reducing or increasing doesn't really matter. We just want the magnitude at this stage. So the change in flux is going to be 7.2 times 10 to the minus 6 Webers. Of course, it's actually increasing. It's gone from 0 to this value, so it's a positive change. So the EMF, using Faraday's law to calculate the EMF, we know that the EMF is going to equal N times the rate of change of flux. And N in this case is just 1 because it's just one loop of wire in the coil. So N just equals 1. And so it's going to be the change in flux, which is 7.2 times 10 to the minus 6, divided by the time. Now the time was 0.02 seconds. And if we work that out, that ends up being 0.36 millivolts. Okay. Now, question 4. In this problem, we had an alternator that was rotating at 50 Hertz. And this is a graph of the EMF being produced by this alternator as it rotates. Now the rate of rotation of the alternator is reduced to 25 Hertz, so it's now spinning at half the speed. What we have to do is graph what we think the new EMF would look like on this graph. Now bear in mind the time scale is the same, so we need to be clear or be careful that we graph it so that the time scale matches. So what are the two things that are going to change? Well, we know that the EMF output of a generator, assuming that we're not going to change the number of coils, that's remained the same, it relates to the change in the flux or the rate of change of flux really. So if we are now slowing the alternator down so that its period is twice as long, that means our value for delta T will be increased by a factor of 2. So now it takes twice as long to actually complete one rotation. So this value has increased. We've increased the time it takes to complete a rotation. In fact, we've doubled it. So what effect will this have on the EMF? Well, we're reducing this fraction, by increasing this denominator, it's going to reduce our EMF. And because we've doubled the amount of time, it's going to halve the EMF. So the first effect is that the EMF, the peak EMF, will be halved. That's the first effect. The second effect is that because the frequency has halved, the period will be doubled. Remember, frequency equals 1 over the period. Alternatively, the period equals 1 over the frequency. So if we have halved the frequency, we have doubled the period. So now you can see that before it took 0.02 seconds to complete one cycle. Well, now it's going to have to take twice as long. So the graph will be stretched out so it completes one cycle in twice the time. But also remember the EMF has been halved, so it'll be more like this. So the graph will look like, if this is the original graph, and it's going to be a rough sketch, obviously, because I don't have a scale, but if the original graph looked like this, if that's the original graph, then the new graph will have half the amplitude and twice the frequency, so twice the period. So it'll only go up that high or down to this value, and it'll take twice as long to complete a period. So it will in fact, where are we? So it'll do something like this. Now, not a great looking sine wave, but I think you get the idea. So that's what the graph will need to look like. Okay, question 5. Oh no, part B, I beg your pardon. Well, we've just explained the reasons why, so you can go back and review that section just to go over those reasons. Question 5. Okay, we had to accurately draw 3 magnetic field lines that are passing through this solenoid. Okay, so let's do that. Now it's positive here and negative at the bottom, and the coil is going around like this. So we've got a solenoid. And this is the positive terminal, and that's the negative terminal. So that means the current is going to be traveling in this direction. That's the direction of our current. And so if we use our right hand grip rule, our thumb points in the direction of the current, and our fingers curl in the direction of the magnetic field. And if I grip this conductor here, or anywhere really, if I grip it there, my thumb's in the direction, it's my right hand, remember, there's my thumb trying to grip the conductor, my finger's going to curl around the back like that. So I'm actually, the field lines are actually penetrating this way through the conductor, through the solenoid. Now the question asks us to complete 3 lines showing the field inside and outside. Now if you just did this, then you're only half right, because all you're doing, you're showing the magnetic field inside the coil. So what you were really expected to do was to show complete field lines like this. And of course show their direction with maybe a couple of arrows like that. And this one. And if it does go too far off the page, then dotted lines may be in order. Okay, but that's what you need to draw something more like that. Now, we've got a rectangular loop. This is the same. This question here relates to this situation here. So inside the solenoid, we've now placed this loop of wire, and this is the solenoid. So the current's still travelling up in this direction. The loop has 3 turns of wire, and at the moment the plane of the loop is parallel with the magnetic field. So this plane here is parallel with the field inside the coil. There's a current of 4 amps flowing through this loop, and the uniform magnetic field strength inside the coil is 5 times 10 to the minus 2 Tesla. So the question is, what is the magnitude of magnetic flux threading the loop? Okay, so let's have a look at these questions. So, the first question, because the loop, I beg your pardon, let's just use a few vectors here. We've got our magnetic field travelling in that direction. That's the direction of the field through the coil. I haven't drawn the coil. So there's our field, and here's our coil inside the solenoid. I'll do that in a different colour. Okay, there's the coil, just a simplified coil inside the this simplified loop inside the solenoid, and its normal is pointing in that direction. So that's the loop inside the coil. Now, hopefully you might remember that flux is actually equal to BA cos theta. Now theta is the angle between the magnetic field line, or the magnetic field lines, I beg your pardon, and the normal to the coil. Now in this case, the angle between B and N is 90 degrees. Okay, that's the angle in there. And so our flux is going to be BA times the cos of 90. Now the cos of 90 is 0. So it doesn't matter what the area of the coil is or what the magnetic field strength is, that is going to equal BA times 0. So it will always be 0. So whenever the normal to the coil is at right angles to the magnetic field, there is no flux. Okay, in the second part, part C, I beg your pardon, we had to work out the force on side PQ. Now PQ is this side here. Okay, so there's side PQ, and there's the other part of the coil. So this is the side here we're concentrating on, right there. And let's see, we know that the magnetic field B is in that direction. We know that the current, let's have a look at the direction of the current. Positive. Okay, the current's going in this direction from Q to P. So I probably don't need the direction, but we'll just do it just to be sure. So that current there is running from Q to P. And so we want the size of the force on that section of the loop. Remember, there are 3 loops or 3 coils to the loop, or 3 turns to the loop. So F equals Biln, B-I-L-N. N is going to equal 3. L is the length of this section of the loop, and that will equal 4 times 10 to the minus 2. I is the current, and that was 4 amps. and B is the magnetic field strength, which is 5 times 10 to the minus 2 Tesla. So all we have to do is multiply those values together. So it's 5 times 10 to the minus 2 multiplied by 4, multiplied by 4 times 10 to the minus 2, and then multiplied by 3, and all of that works out to 2.4 times 10 to the minus 2 newtons. That's newtons, because it's after the force, of course. Okay, so that was that part. The final section to this question, part D, let's have a look. Part D, what is the force on side QR? Well, QR is this side here. Now notice that this side here is parallel to the magnetic field inside the solenoid. Now, F equals BILN, but if there's an angle involved, it's sine theta on the end. Not cos theta like the flux formula, this is sine theta. And theta is the angle between the current and the magnetic field. So this theta here is the angle between the current, the direction of the current, and the magnetic field. So if you remember, as we just pointed out, the current is running in this direction, the magnetic field is running in this direction. So the current and the magnetic field are parallel. The current and the magnetic field are parallel. So that means if I drew my current in that direction, and my magnetic field is also in that direction, then the angle between them is 0. So theta equals 0. And the sine of 0, the sine of 0 is 0. So sine of 0 equals 0. And as a result, this whole thing here is going to equal 0. So, because sine theta equals 0 in this case, then BILN will also equal, no matter what that comes out to be, you're multiplying it by 0. So the force is going to be 0. There is no force on that section of the wire. So the only force is on this end and on this end. The parallel sections, the sections parallel to the field, experience no force. Right, moving on to the next question. All right, we have a coil with slip rings rotating in a magnetic field in a clockwise direction, and we note that I forgot to put in the magnetic field strength here. It is in fact 2 Tesla. Okay, so the information is the frequency is turning at 50 Hertz, the area of the loop is 3 times 10 to the minus 4, and there are 50 turns of wire. They haven't been shown, but there are 50 turns there. Now let's have a look at the questions. First question is calculate the magnitude of the change in flux as the coil rotates 90 degrees in the clockwise direction. Okay, so it's going from the position at the moment, because the normal is parallel. The normal to the coil is parallel to the magnetic field. It's going to be maximum flux. Okay, so what we really need to do is just work out what that flux is. So let's do that. So the maximum flux, when the coil is in that position, the initial position, is simply going to be the magnetic field strength multiplied by the area. and that's going to be 2, which is the magnetic field strength, 2 Tesla. The magnetic field strength in this problem equals 2 Tesla. Multiplied by the area of the coil, which is 3 times 10 to the minus 4, and that equals 6 times 10 to the minus 4 Webers. So it's gone from this value to 0 in quarter of a turn, and so the change in flux is the final flux, take away the initial flux, which is going to be 0 take away 6 times 10 to the minus 4, which is actually equal to negative 6 times 10 to the minus 4, but the question only asks for the magnitude, so we can negate the negative sign. We don't have to worry about the negative sign for this particular problem. Okay, the next part of the question, probably more difficult. During this interval, what is the direction of the current flow through the coil? Is it in the direction UVWX or XWVU? So what it's asking, as it rotates from this position around, so it's now appearing flat, it's rotating in the clockwise direction, quarter of a turn, will the current in this coil, will it be going in this direction? That's XWVU, or will it be going UVWX? So which way will the current be going in the coil? And, pardon me, whenever we want to work out the direction of current in a generator problem, or whenever there's a current being induced, we use Lenzs law. So let me show you how we do this. So we're going to use Lenzs law. So let's have a look. I'll draw a series of diagrams that might help us to visualize this. Now, the first situation, the coil was looking like this. And the field was traveling through the coil like that. And that's X, W, V, and U. It now rotates in the clockwise direction, so it now appears to be like this. So it's now looking flat. And this W is now there. This is X, this is V, and this is U. So it's rotated 90 degrees in that direction. So we need to work out which direction the current is through the coil. So we're going to use our 4-step process. The first step in the process is to look at use vectors, remember, to look at the direction of the initial flux. So, just one more thing before I do that. I want to put in a vector which shows us the normal to the coil, and this is where it gets really useful. There's the normal to the coil. There's the normal to the coil. And I just need to put in my magnetic field vector there. So that green one is the magnetic field strength. So you can see this is the initial situation, and this is the final situation. So because we've mapped, or we've drawn the normal vector and the magnetic field vector in both diagrams, we can now see the relationship. So what I'm going to do is now draw the 4 steps with the normal in mind. So I'll go to white. So initially, the initial flux my normal, I'll draw it, actually, sorry about that. Normal's in that direction and flux is in that direction. Okay? The final flux arrangement, the normal, now we're looking in relation to the normal, so I'm going to draw the normal in that direction. So we're looking at the magnetic field in relation to the normal. Well, the magnetic field is now at right angles to the normal, so the flux is actually going to be 0. So here the flux is 0. Now the change in flux in relation to the normal, initially there was a flux flowing through it, now there's no flux. And so it's a negative change, isn't it? So the actual change in relation to the normal, if that's my normal in that direction, then the vector that represents the change in flux as far as the normal is concerned is in that direction. Because as far as the normal is concerned, it was initially had a flux flow going through it, and now there's nothing. And so as far as the normal is concerned, the flux is reduced. It's reduced to 0. So the final flux, sorry, I beg your pardon, that was the initial, the final, now the change is that. Well, the final step is the induced flux. This is our 4-step process, the induced flux, and the induced flux will always be in the opposite direction to the change in flux. And so it will be, in fact, this direction. So that's the direction of the induced flux. That's the induced flux in that direction in relation to the normal. So this is quite can be quite challenging for some people. So let me just go through it quickly one more time. The key here was to show what the magnetic field, what the flux is doing in relation to the normal. So I show the normal in both sets of diagrams. And so here they were parallel, which is what we did in this first diagram. Here, as the coil rotates, the normal is moving. The magnetic field, the flux lines don't change direction. And so now, as far as the normal is concerned, the flux is 0. As far as the normal is concerned, it went from a maximum value going in this direction to 0, so that represented a negative change in flux, or in other words, the change in flux is being reduced compared to the normal, and therefore our induced flux is going to be opposite to this change. So the final step is we take this particular vector here and we use our right hand grip rule to determine the direction of the current. And the way we do that is that we use our right hand and we grip the coil so that our fingers are in the direction of the induced flux. So, in the direction of this arrow in relation to the normal. So, let's use this one here. I need to stick my hand in this coil so that my fingers are pointing in the direction of the induced flux in relation to the normal. There's my normal there, and there's my normal there. Okay? So, in relation to the normal to the coil, I need to stick my fingers so that they are going in that direction. In other words, my fingers are going in that direction. I'm poking my right hand so that my fingers curl around and stick through the conductor in that direction. And if I do that with my right hand, my thumb, if I grip this, my thumb is pointing along the conductor in that direction, there. So my thumb points along there, which is the direction of the current. So the current's going to go from UVWX, from UVWX. That is the direction of the current. So the answer was direction UVWX. Okay. And in part C, which one of the graphs in figure 6, which is this set of graphs down here, best represent the correct relationship between the induced voltage in the coil and the magnetic flux through the coil as observed on the oscilloscope? Okay, so now notice that the generator has slip rings. Now that tells us that we're going to, if this is going to produce a sine wave current inside the coil, then we're going to get a sine wave output. It's not going to be reversed or chopped off because the slip rings preserve what's going on inside the coil. If this was a commutator, a split ring commutator, we would end up with a different result. Pardon me. So, let's see which one of these it's going to be. Now, remember the EMF is related to the negative rate of change of the flux. So, in this particular graph, the EMF, beg your pardon, the flux is the dotted line. So it's actually a cosine graph. So I'm going to draw my flux graph first. Now I'm going to do it like this, just so you can understand the reasoning. Of course, you will find a much quicker way to do this in an exam environment, but I just want to make sure you are clear on the logic behind it. Okay, and I'll just give myself a time scale. And what I'm doing here, I'm showing how the EMF graph is derived from the flux graph. So I'm going to draw the flux graph first, and we'll do that in white. And here it is, the cosine graph. And it's going to do that. And it'll just continue doing that as it keeps rotating. So that's our flux graph. There's our flux. Now, the next graph is a graph of the change in flux, because remember the EMF is related to the change in flux. So this graph will be change in flux over time, of course. Now, what this represents, if this is the flux graph, this is the gradient, a graph of the gradient of that graph. So in other words, we get this graph by looking at the gradient of this graph. So here, I'll do this one in green, here the gradient is 0, and it's also 0 here, and it's also 0 here. So that means this graph is going to be 0 at that point, and that point. At this position, this is where the gradient is steepest and negative. So this will be where it's maximum and negative. Here it is steepest and positive. So steepest and positive there, steepest and negative there. So you can see that our change in flux graph looks like this. Now, the next step is that we know the EMF is actually related to the negative rate of change of flux. So it's going to be the negative of this graph. So what we then need to do, this next graph will be the same as this graph, except it's inverted. In other words, this will be the negative rate of change of flux. And so where it's negative here, it'll be positive here. So this is simply reflected. So it does this. And that becomes our EMF graph. So our EMF graph will be simply this. So it's going to be the sine graph. There you go. Pretty bad looking sine graph, but never mind. So we're looking for the option where the flux is a cosine and the EMF is a sine graph. So let's have a look at our options. Okay, here it's option A. There's our flux graph and here's our voltage graph. So the correct answer is option A. That was the answer. So option A. Okay. What's happened there? It's all spun out on me. Right, okay. All right, sorry about that. Moving on. Okay, in this question, we've got a coil in a magnetic field, and the voltage being induced is being created by a time-dependent magnetic field. In other words, the magnetic field is changing over time. Okay, this magnetic field is changing over time. And so, as the magnetic field changes, of course, the flux through the coil will change. And here is a graph of how the magnetic flux varies with time. Here. Okay, so this graph shows us what the flux is doing through the coil over time. So what do we have to do? On this set of axes, we have to provide a sketch of the EMF against time as it appears on the voltmeter. Okay, so remember, this is not as hard as it looks. The key thing to remember is that there's 2 points. There's 2 points to remember here. The first point is that you'll only get an EMF, there will only be an EMF value when the flux is changing The second point is that the EMF will oppose the change in flux. So in other words, if it's related to the gradient, the negative of the gradient of the flux. Let me explain that a bit more. So here, this gradient here, that's showing a change in the flux, and that's an increasing flux. Over here, this is a decreasing flux. So it's only in this section here and this section here that we're going to achieve, that we're going to see any EMF. In this section, this flat section here and this flat section here, there will be no EMF at all. But the point I was trying to make was that this is an increasing flux, so this will cause a specific change in EMF, but here it's a decreasing flux, so the EMF here will be in the opposite direction to in this section here. The other thing to note is that the gradient here is twice as steep as this gradient here, indicating the rate of change is twice as rapid as it is over here, so the EMF will be twice as large in this section than it is in this section. Okay? So, in the first section there will be nothing. So, let's try and draw this. And once again, this will be a fairly rough sketch because I don't have the grid, but hopefully you'll certainly see the idea. Right. So in the first section, there's no EMF at all. So this is a graph of the EMF over time. And in the first section, there is nothing happening. So no EMF. And just to reiterate, here the flux was not changing. So over the first 5 milliseconds, there is no change in flux, therefore there is no EMF. Between 5 milliseconds and 10 milliseconds, there is an increase in flux, and it happened at a quite substantial rate. So during this time, there is an EMF. And because the gradient is constant, the EMF will be constant. So that means that for this section, I'll just draw a dotted line there, for that section there, for that 5 millisecond period, there will be a constant EMF value. So this is at 5 milliseconds, that's at 10 milliseconds. Now, so between 10 and 15 milliseconds, it's a constant flux. Constant flux means no change in flux, which means no EMF. So between 10 and 15 milliseconds, there is no EMF. So between 10 and 15, it'll be back to zero, doing nothing. There it is there. So now we're at 15. Now, between 15 and 30, the EMF will be half the value as it was in this section because it's changing at half the rate. That gradient is half of this gradient. And also because this is a positive gradient, this is a negative gradient, this will be in the opposite polarity than it was in this one. So in my graph then, for 15 to 30 milliseconds, the EMF will be of the opposite direction. So if this was negative to begin with, then this will be positive, but it will only be half the value. So it'll be a constant EMF of half the value of that. Now you didn't need to actually have a value there, as long as on the graph this distance here is half of that distance. Bear in mind also that this had to be 15 milliseconds in length, this had to be 5 milliseconds in length. So that was the answer to the problem. Alternatively, if you had this arrangement, this would have also been deemed as right. If you had nothing and then That is also, oops, shouldn't have done that part. That is also correct, because it didn't actually specify which direction you need to start from. Okay, next question. Part B, the magnetic field is now reduced to zero over a period of 10 milliseconds. What is the average EMF induced in the coil during this 10 millisecond interval? And show you working. Okay, so if you look at the problem, you are told that the coil has 100 turns of wire, so N equals 100. We're also told that the change in flux was, pardon me, I'm just really turning back. There it is, sorry. It's the flux, I beg your pardon. The maximum flux through the coil is 2 times 10 to the minus 4 Webers. That's the flux. And so we don't need the area in this problem because we've already been given the flux. The only other thing we need is the time interval, which is 10 milliseconds, which is in fact 10 times 10 to the minus 3 seconds. Okay, so our EMF is going to, using Faraday's law, it's going to be N times the rate of change of flux. So it's going to equal 100 times the change in flux, which is going to be what's gone from, it's rotated, it's gone from this value to 0, and so it's actually a negative change, but we only want the value of the EMF, so the signage isn't important. So it's going to be 2, or we'll put it anyway, it doesn't really matter, but 2 times 10 to the minus 4 because it's reduced, divided by the time, and the time is 10 by 10 to the minus 3. And so if we work all that out, the answer ends up being 2 volts. So that was the average EMF. Okay, part C. As the field is being reduced, in what direction is the current flowing through the ammeter? Now this is very similar to the previous problem we did. So here's our coil. We have to work out which way is the current going in the coil. Is it going through the ammeter P to Q, or is it going through the ammeter from Q to P? And we're told there's actually, let's check something. The magnetic field is now reduced to 0. Okay, so it's reduced from this value to 0. Okay, so let's work this out. So once again, we're going to use Lenz's law. And we're going to use the 4-step process. Sorry, I'm just rotating. Can't quite work out why I keep rotating this screen. Okay, so in this problem we've got our coil. This is the coil inside the magnetic field. and the normal to the coil is in that direction. And initially, the flux is in that direction also. Okay, so that's the initial situation. The final situation is that the flux now drops to zero. So here's our coil. Coil hasn't moved, so the normal's still pointing in that direction, but now the flux is zero. The final flux is zero. So in relation to our normal, then the flux has gone from some maximum value to zero. So it's actually reduced in relation to the normal. So therefore, our change in flux, which is the final flux, take away the initial flux, is 0 plus the negative of the initial, which is that's our initial flux. Well, the negative of that is going to swing it around, so it's going to be 0 plus that, which equals that. So there's our change in flux. Okay, finally, the induced flux. Remember, it's our four-step process: the initial flux, the final flux, the change in flux, and finally the induced flux. Now remember, the induced flux will always be in the opposite direction to the change. So our induced flux will be in that direction. So now all we need to do is to, if you remember from our previous problem, we now need to use our right hand grip rule and then place our fingers or thread our fingers through the loop of wire so that our fingers point in the direction of the induced flux. So the fingers have to point in the direction of the induced flux inside the coil. So I need to imagine getting my right hand and sticking my fingers, gripping the conductor, but sticking my fingers so they're going in through the coil in this direction, through the coil like that. And so if I do that with my right hand, my thumb will point in that direction. That's the way my thumb would point if I'm gripping it with my right hand, and so that is the direction of the current. And that corresponds to, if we trace this back, that means it's going that way. So which means through the ammeter, it's going to be going from Q to P. So it's going this way around like that from Q to P, Q to P. And that was the answer. Righto, our final lot of questions, I think, on transmission. Okay, so let's have a look at these. Now, the first question, we've got a transmission system, we've got a generator, we've got the power at 20 kilowatts producing a voltage of 400 volts. The power goes firstly through a step-up transformer, and then it's transmitted across a significant distance, and then it goes through a secondary transformer, which is the step-down transformer, and then finally it's used in a lighting circuit. So let's answer these questions. The first point is a step-up transformer will reduce the electrical energy lost over the transmission lines. We have to explain why. Why does a step-up transformer reduce electrical energy lost over the transmission lines, which is over this section here? So, the points we need to consider for this question. The step-up transformer what it does, it will it will increase voltage and reduce current. And it does that because the power inside the transformer must remain constant. So if V goes up, I has to go down. Now, the next logical step is that now that the current's been reduced, that's the important part, we're reducing the current. The second point is this. That means less current flows through the transmission cable, less current through the transmission cable. The next point, of course, is that the loss of power, loss of electrical power through a transmission cable is related, P lost, is related to I squared times R. And so by reducing the current, we are going to reduce the power loss. So your answer had to have those three, basically have those points. You need to talk about the fact that the step-up transformer reduces the current and increases the voltage, maintaining a constant power, less current through the transmission cable, and therefore, because power loss is related to I squared R, this will mean that implies less power lost. The second question was relating to explaining why a transformer cannot work with a DC current. Okay, transformer cannot work with DC, okay? It's not asking you to explain why it can work with AC, it's asking you to explain why it cannot work with DC. So the starting point will be that the transformer, any transformer, relies on Faraday's law to induce currents, and that equals N times the rate of change of flux. And as a result, the EMF, to induce an EMF, we require a change in flux. So to create an EMF, a changing flux is necessary. Okay, with DC, this is the next point, with DC there is no change in current. Oops, sorry about that. No change in current, and therefore there is no change in corresponding flux. In primary coil, therefore there will be no change of flux in the secondary coil of the transformer, and therefore there will be no induced current or voltage in secondary coil. So it was important to give the basis of your theory, in other words, the physics that underlies your explanation, but your emphasis need to be on why it won't work with DC. This is an example of where the exam will try to stop people using their stock standard written responses they have already written out on their cheat sheets, and that's what they'll be awake up to. So you need to read your questions carefully and make sure you address the question. Okay, it might only require a slight tweaking of your answer, but you do need to make sure that your answer is a response to the question they've posed, not a generic. Do not write in generic answers. Okay, no generic answers. Rightio, so there's those two questions. And finally, we've got some calculation questions. And they are, calculate the following. We had to calculate the current in the transmission cables. Okay, let's do it. They're very sensitive, this. Okay, so part C was the current. In the transmission cables. Current in transmission cables. In order to do this, we use our transformer formula, where we know that the ratio of coils to the secondary to the primary is going to equal the ratio of the voltages between the secondary and the primary, and that will equal, try that again, I'm sorry, V primary, and that will equal the inverse ratio to the currents. So it'll be IP on top and secondary on the bottom. So just remember that the current ratio is the opposite to the voltage ratio, and the voltage ratio is the same as the coil ratio. So the part that we're using to solve this problem is we're linking this part to this part. So we know that the ratio in the step-up transformer is 10 to 1. So NS in this problem, this number of coils in the secondary was 10 compared to the primary of 1, or the ratio is 10 to 1. Therefore, we know that, just substituting these values in, we know that 10 over 1 is equal to IP over IS. Multiplying both sides by IS, that means that IP, the primary, I beg your pardon, what the secondary current, IS will equal IP over 50, pardon me, over 10. So what we need to do is work out what IP is. What is the value of IP? In order to do that, we need to go back to the part of the problem. We know that the power at the generator is 20 kilowatts and the voltage is 400. So at the generator, we know that power will equal 20 kilowatts, or 20,000 watts, and the voltage is 400. So using P equals VI, we can now work out the primary current, and that will be I equals P over V, which is 20,000 divided by 400, and that equals 50 amps. So now we can work out our secondary current. IS is equal to 50 over 10, which is 5 amps. And that's our answer, 5 amps. Okay, the next question was the voltage drop across the transmission cables. Okay, so here's the first transformer. Here's the second transformer. And here are our cables. linking the two. Now we know that the total resistance of these cables is 5 ohms. 5 ohms, there we go. And we know that the current flowing through this transmission line, we just worked it out in the previous problem, the current is going to be 5 amps. Now we should just pause here for a second. This current, because we're actually dealing with alternating currents here, this current will be an RMS value. So to be perfectly correct, our currents and our voltages here will all be RMS. Now that won't change our calculations, it just means that it's like an average value of the current, but the current is in fact an alternating current. But this is the RMS value of that. So our RMS voltage drop across the transmission lines will equal, using Ohm's law, I times IRMS times the resistance, which is going to be 5 times the resistance 5, which is 25. So the voltage drop is 25 volts. And as I said, it's actually RMS, although that wasn't specified in the problem. So the voltage drop from here to here is 25 volts. That means, of course, that whatever the voltage is at this point in the circuit, it's going to be 25 volts less by the time it gets here. So it's going to be 25 volts less at this end. And that's important, I think, for the next part of the problem. For the last part of the problem. Okay, part E is the percentage of electrical energy produced which is converted to heat down the transmission lines. Okay, so we know that there is a certain amount of energy lost as current flows down these transmission lines, and that lost energy, we know the power lost is equal to I squared R. Okay, so let's work out the power lost. So it's going to equal 5, the current is 5, so it's going to be 5 squared multiplied by 5. So it's 25 times 5, or 125 watts. So that's the power that is lost due to heat as the current runs down the transmission line. So what percentage of power loss is that? Well, the percentage power lost will equal the power lost divided by the power we started with, the power at the generator, times 100 over 1, or just times 100. So it's going to be 125 over the initial power, which is 20,000, times 100. And so that ends up being 125 over 200, which is 0.625%. So less than 1% of the energy in this, of the power and the energy in this problem, is being lost in the form of heat, and that's a pretty good rating, I have to say. Okay, final question. I think we're up to the final question. Yep, we are. Beautiful. Okay, so last question. The voltage which is available at the lighting circuit. Okay, so now we know, let's draw a circuit again. We know that there's our generator. I'll draw the generator again, and that goes to a transformer, T1, and then it goes to a second transformer, T2, and then it goes to the lighting circuit, L. Okay, We're assuming there's no power loss in these cables, and there is a power loss in the transmission cables. Okay, so let's have a look. Now, we have to work out what's the voltage arriving here first. Well, we know that 25 volts is lost. Remember the voltage drop across the transmission cables. 25 volts is lost down the transmission cable. Okay, so that's lost. So if we know what it was here, we can work out what it is here. The question is actually asking what it is at this point for the lighting circuit, so we'll get to that in a second. Okay, so we know that at the generator it was 400 volts. That was the initial conditions, and the power was 20,000. We don't need the power anymore, but we'll just put it there. 20,000 watts, 400 volts. Now this was a step-up transformer, which means, and it was 1 to 10. So that means the voltage is going to be pumped up by a factor of 10, whilst the current went down by a factor of 10. So that means that by the time the voltage gets to here, it's going to be 4,000 volts. Another way of looking at that, of course, is that the ratio of the windings, secondary to primary, is equal to the ratio of the voltages. And so the secondary voltage, Vs, is going to equal Ns over Np times Vp, which is going to be Ns, that's 10 on this side, that's Ns side, and that's 1, that's the primary side. So it's going to be 10 over 1 times the primary voltage, which is 400. So that will actually equal 4,000 volts. Okay, so that's our voltage here. So it gets to here, 25 volts is lost. So at this point, it's actually 3,975. 3,975 volts. But what happens here? It goes through a step-down transformer. Step down. Now, the step-down transformer is the same ratio except in reverse. It's going from 10 to 1. So whereas here, the voltage increased by a factor of 10, here it's going to reduce by a factor of 10. But it's not 4,000 anymore, it's now 3,975. So the voltage here is going to be 397.5 volts. In other words, this divided by 10. And to do that using the calculation method, we'll just to confirm it, once again, the ratio of turns in the transformer, Ns over Np equals Vs over Vp. Now we're trying to work out the secondary voltage for this step-down transformer. So remember, this time the ratio is 10 to 1. So this is going to be 10 and this is going to be 1. And we're trying to work out the secondary voltage. That's what we want. And we know that the primary voltage is 3,975. So therefore Vs will equal Ns over Np times Vp. There should be an N, by the way. And that, of course, will equal 1 over 10 times 397.5, which is going to be 397.5. So 397.5, and that's the voltage, because no voltage was lost across here. No voltage lost. Okay, so whatever the voltage was there, it's going to be there, and that's the voltage available for our lighting circuit. Okay, so that's our SAC covered. Hope it helped.